We're going to continue our discussion of crossing numbers of graphs. So remember, we're trying to find how you can draw a graph to have the fewest edge crossings possible. And in particular, we would like to know how to prove that some graph must have many crossings. The extreme case in the other direction was planar graphs, and planar graphs can be drawn with 0 crossings, but it seems that we should be able to find ways of guaranteeing that there are many crossings. For non-planar graphs, we know there should be at least 1, but I think we could do better in terms of lower bounds. So let's start with this. First, the upper bound we started with last time was that the crossing number for g was less than n to the 4th. And we were a little sloppy. We cut out some factors of 2. You might write this a little bit more carefully, something like 1/4 n to the 4th. So that's our upper bound. We know there's not more than that. But is the situation really that bad? For example, K5, a complete graph, at first we drew it with 5 crossings, but with a little cleverness we got it down to just 1 crossing. Let's see what we can do. Here's a first idea. Let's use Euler's formula for planar graphs. And even though G might not be planar, it still tells us something important about planar graphs. Remember, a planar graph, a maximal planar graph, has 3n minus 6 edges. So if you have more than 3n minus 6 edges, then the graph is not planar. Right? M greater than 3n minus 6 implies not planar. And so there must be at least 1 crossing. Okay, that gives us a case where just some condition on the number of vertices and the number of edges gives a lower bound on the crossing number. And it holds within it the seed of a slightly better bound. Okay, because actually, after you've added 3n minus 6 edges, you know that every new edge is going to have to introduce a crossing. So if you took the maximum set, or the, even a maximal set of edges that don't have any crossings, there's at most 3n minus 6 of those, and everyone after that is going to cross some other edges. So after the first 3n minus 6 edges, and again, you have to be careful about how you order them, but you order them, you do as best you can to not introduce crossings. And at some point up to or before 3n minus 6, you will start introducing crossings with every edge you add. And so putting this together, we get this bound, which is just saying that the number of edges minus those first 3n minus 6, every one of them gives at least 1 new crossing, and so that is a bound. Let's look at how good it is. So if I took a graph with, say, at least 4n edges, so if m is bigger than 4n, then it implies that the crossing number is bigger than something like 4n minus 3n n plus 6. Let's say it's bigger than n. So I can guarantee now a linear number of crossings as long as I have this number of edges, which is actually still linear, could still be linear in n. All right. In the more extreme case, if I took m to be something quadratic, so like almost a complete graph, it's a really dense graph, something like n squared, then I'm going to get a crossing number bound. Again, this is a little bit sloppy because it's only up to some constants here, but it's going to be something also like n squared. Maybe I should put this as omega of n squared, lower bounded, up to some constant. So n squared, or n squared over 2, or even n squared over 3 minus 3n asymptotically looks like n squared. And so I get a quadratic number of crossings, which seems great. It's much stronger than our bounds from the last picture, which was just 1. But there's a big difference between n squared versus the upper bound, which is n to the 4th. So in order to get a bound, a lower bound on the crossing number that is bigger than quadratic, I'm going to need a new idea. And I'm going to show you a proof that's quite beautiful, quite surprising, and uses a really clever idea. So here's how you might do this. So here's the theorem first. The theorem is, if I have at least 4n edges, then the crossing number is greater than or equal to m cubed over 64n squared. And at first, this is a little bit, I think, not obvious how this relates to our other bounds, but let's plug in some values and see if m is like n squared, then I get something like a crossing number of n to the 4th, because n squared cubed is n to the 6th over n squared. It's like n to the 4th. So that means that this, in the dense graph case, is going to give me a lower bound which does look like n to the 4th, which was as bad as it could get also in the worst case in our upper bound. So we'll have matching upper and lower bounds. And if I took some other examples, I guess if I took m to be like n to the 4/3, n to the 4/3 cubed is n to the 4th. Here I would get a crossing number that was something like quadratic. So before, I had to have a quadratic number of edges to get a quadratic lower bound. Here it shows that there's going to be a quadratic number of crossings, even if I only have, say, n to the 4/3 edges. Okay, so the idea is we're going to take our graph G and we're going to take subgraphs of G. So H is going to be a subgraph of G, and it's going to be an induced subgraph. And the way we're going to form it is just pick a random subset of vertices. So for every vertex in G, we pick a probability P equals 4n over m. And we keep that vertex with exactly this probability. Now this looks like magic right now, but you'll see that this turns out to be exactly the right choice to get the bound we want. But before I go into how we use it, let me explain the key idea. You see, our old bound, using Euler's formula, I'll call that the Euler bound, Euler formula bound, was only good for sparse graphs. That is, good as in tight. And we saw that for dense graphs, it was clearly way off. So if G is not sparse, and we want a better bound, a bigger lower bound on the crossing number, it makes sense for us to find sparse graphs inside G. And so once you sample the vertices with this probability and take the induced subgraph, you're going to end up with a sparser graph. And so H will be sparser. We can apply this Euler formula bound, it's Euler type bound, and then use probability to bound the crossing number of the original graph. Okay, so this is just the high-level idea of the proof and like why this might ever be a good idea. And once you set up this process of forming subgraphs, you can pretty immediately make some strong statements about what you expect to see in the graph H. Here's what I mean. if I were to ask how many vertices does H have, and let me also, before I do anything, remind you what the probability is. It's 4n over m, is that right? Yes. And so if I sample each vertex and keep it with this probability, then I expect to see p n vertices, right? There were n vertices in the original graph. Every one of them stayed around with probability p. This is how many vertices I expect to see in the new graph, right? This is the expectation of this random variable because the graph h is randomly defined, and so the expectation is the average overall random choices of what I expect to see. Now, the expected number of edges, well, every edge in G will continue to be in H if and only if we kept both ends. And since we kept each vertex with probability p, we did them all independently, this is going to be p squared times m. So for each edge, we look at the probability that we kept both ends. Now, the expected number of crossings is going to be p to the fourth times the crossing number of G. Why is that? If we take the best possible drawing for G, that is the one that minimizes the number of crossings, each one of those crossings is going to involve 4 vertices. So if all 4 of those vertices remain, then if we took the drawing of H we get as a sub-drawing, if you will, of the drawing of G, then that crossing will remain. So this, right, p to the fourth here, is the probability we keep all 4 vertices. All right, now we're ready to bound the crossing number of H first. Remember, our Euler bound was what? That it was bigger than the number of edges in H minus 3 times the number of vertices plus 6. So we could just write this directly as the number of edges in H minus the number, minus 3 times the number of vertices in H. And the constant just makes it a little even stronger. So the crossings in G have to be at least, just from this formula here, if we move it to the other side, this is 1 over p to the fourth times the expected number of crossings in H, which we just saw was bounded as follows. If I were to plug in this number of edges minus 3 times the number of vertices, and inside the expected value here, I can use this standard fact, which is the linearity of expectations, to break it into 2 parts. So this is the expected number of edges minus 3 times the, let's write it like this, the expected number of vertices. And now I can plug in my values for these. This is then 1 over p to the fourth, p to the fourth, sorry about that, of the expected number of edges, which was p squared times m, minus 3pn, and plugging in this value for p and canceling everything out is going to give me, I could do it out if you like. Maybe I'll time lapse this. It just comes out to exactly the bound we claimed in the theorem, 64n squared, and the denominator m cubed over 64n squared. So it's sort of this is a bit of a surprising proof, It actually appears in a book called Proofs from the Book, which is a reference to the great mathematician Paul Erdős had this idea that certain proofs were so beautiful that they were the perfect proof for a given statement, and they were written in this book, and God had this book, and sometimes, every once in a while, humans would discover a proof that came from this book. And so someone went through and found the best proofs, they thought, and wrote a book called Proofs from the Book, and this one appears there. It's a classic, clever idea of using a bound for sparse graphs and applying it to general graphs by this random process. Very, very cool idea.